Okay, so good morning, students. So let me share the slides. Okay, so last time we have started with the joint distribution. So now we know the conditional distribution also we have defined. So we can find out basically the conditional distribution of y given x is equal to x. And from there we can find out expected value of y given x is equal to x also. Okay, so this will be nothing but integration y and conditional dy. Okay, so this will be some function of x, small x. Okay, so now if we replace this small x by random variable x, then that means this is nothing but expected value of psi of x, random variable x, replacing this small x by capital random variable x. And if we take the expectation here, expectation will be over this, then this will come out as expected value of y basically. So in this fashion, we let me just write down the general result. So expected value of x given y is equal to expected value of x. So proof, let me just show you. So expected value of x given y. So you know that as we have just seen, this will be function of some psi of y. So if I expectation, this expectation is over basically y. So therefore, let me take that if discrete variables are there, so then this will be summation over y. Expected value of x given y is equal to small y into the density of y. Okay, so this will be like this. Okay, so now what is this value? This is expectation of x given y is equal to y. So uh, this will be because density will be corresponding to f of x given y. So this will be summation over x p x given y is equal to small y x into p y y. Okay, where p y y is the marginal distribution of y, and p of x given small y is conditional distribution of x given y is equal to small y. So therefore, this value will be uh, summation y, summation x will be here, summation, let me take x here, y here, and this value is nothing but joint over marginal of y into p y y. Okay, this will cancel out. So therefore, this will be summation over x. Now we are summing joint over y. What we will get?
Marginal of x.
Yes, so we will get marginal of x. So therefore, this will be summation x px. So this is expected value of x. So therefore we have shown that expected value of x given y is expected value of x. So so in the same fashion, you can show this also, second one also, expected value of gx given y is expected value of gx, where g is okay. So for example, gx may be x square, x cube also. Variance of x can be written as expected value of variance of x given y plus variance of expected value of x given y. So proof will go in the same fashion. Now, now let us define the linear combination of random variables. So x1, x2, xn be the random variable. Xi, random variable xi has mean mu y and variance as sigma I square, and a naught, a1, an are real valued constants. Then let us say we define y is equal to a naught plus summation ai xi. That means some linear combination basically. Okay, so then so y we are defining as a naught plus summation ai xi, I is from 1 to n, and ai basically some values are there, numerical values, and let us say the mean of xi is mu I and variance of xi is sigma I square. Then we want to find the mean and variance of y. So what will be the mean of y? So therefore this will be expectation of a naught plus summation ai xi i's from 1 to n. So this will be, because n variables are there here. So uh, for example, let me give the proof for 2. Expectation will go basically inside a naught plus summation i's from 1 to n ai expected value of xi, which is nothing but mu I. So this will be a naught plus summation ai mu I is from 1 to n. So for example, if y is a naught plus a1 x1 plus a2 x2, then expectation of y will be expectation of this. So therefore this will be, let me take the x1 x2 are basically discrete, then summation x1 x2 a naught plus a1 x1 plus a2 small x2 into joint of x1 x2. So a naught plus double summation joint density, that will be 1, plus a1, then this will be summation x1 into summing the joint density over x2, that will be marginal of x1, plus a2 and summation x2 and summing the joint density over x1, we will get x2. So this will be mean of x1, definition of mean of x1, and this is the definition of mean of x2. So therefore this will be a naught plus summation a1 mu1 plus a2 mu2. Okay, in this fashion we can obtain this. Now if let us say that additionally we assume that if x1 x2 xn are independent also, then variance of a naught plus summation ai xi, I is from 1 to n, will be summation ai square variance of xi, I is from 1 to n. That means this will be summation ai square sigma I square, I is from 1 to n. So what will happen to basically in general? Okay, if they are, we are assuming that they are not, they may not be independent. So then let us say that I want to find out the variance of y, which is variance of a naught plus a1 x1 plus a2 x2. Let me take y as this value. Then what is the definition of variance of, let us say, x? Can anyone define variance of x? How variance of x is defined in terms of expectation?
Expectation of x minus mu square whole square.
Yeah, so this will be expectation of x minus mu square. Okay, so that means this value is nothing but expectation of a naught plus a1 x1 plus a2 x2 minus expectation of a naught plus a1 x1 plus a2 x2 square of this. So this will be expectation of a naught plus a1 x1 plus a2 x2 minus a naught and minus a1 expectation of x1 minus a2 expectation of x2 whole square, because of the previous result also. So a naught will cancel out. So therefore this will be expectation of a1 x1 minus expected value of x1 plus a2 x2 minus expected value of x2 whole square. So this will be expectation of a1 square x1 minus expected value of x1 whole square plus a2 square x2 minus expected value of x2 whole square plus 2 times a1 a2 x1 minus expected value of x1 x2 minus expected value of x2. Okay, then expectation we can take inside as we are doing previously also in the same fashion as we are doing here. So therefore uh, this will be a1 square expectation of this value. If I take expectation of this value, what we will get?
Variance of x1.
Yes, so this will be variance of x1. So that will be sigma 1 square I can write down. And so you can write down variance of x1 also if you want. So that is the same thing. So variance of x1 plus a2 square variance of x2 plus 2a1 a2 expectation of this. That is the covariance between x1 and x2. That is the definition of covariance between x1 and x2. So therefore, in general, for a linear combination, variance of a naught plus summation ai xi, I is from 1 to n. This can be written as summation ai square, variance of xi, I is from 1 to n, plus 2 times double summation I over j, I is less than j, ai, aj, covariance between xi comma xj. So this will be the general formula. In the same fashion we can derive this. So when x1, x2, xn are independent, then that implies that covariance between xi and xj are 0. Okay. So if that is independent, then if they are independent, then we know that last class we have done that if x1, x2 are independent, this implies that covariance between them is 0. So therefore, this relationship will hold, summation ai square variance of xi. If variables are uncorrelated, then also covariance, uncorrelated means covariance between them is 0. Then also covariance will be 0. They may not be independent, but if they are uncorrelated, then also covariance is 0. So let us take this example. A petrol pump sells petrol, premium petrol and diesel. Their prices are rupees 80, 90, 60 respectively. X1, X2, X3 denote the amount of petrol, premium petrol, diesel purchased on a particular day. Let X1, X2, X3 are independent with the mu1 as 1000, mu2 300, mu3 500, and sigma 1, their standard deviation are 100, 80 and 50. The revenue from the sales. So because we are selling the petrol at 80 rupees, so 80x1, 90x2 plus 60x3, then mean revenue from the sales will be 80 mu1, 90 mu2 plus 60 mu3. So therefore, just plugging in the value of mu1, mu2, mu3, we will get this value. And variance of y is nothing but 80 square sigma 1 square, 90 square sigma 2 square, 60 square sigma 3 square. So just plug in the values of from sigma 1, sigma 2, sigma 3, sigma 1 square, sigma 2 square, sigma 3 square, we will get this value. So therefore, this is the answer for variability of y. Okay. So now let us define for the x1, x2, xn are independent random variables. Then let us define some Sn as summation xi. Then mgf, moment generating function of Sn, will be expected value of t raised to power Sn. So now it can easily be shown that this is product of moment generating functions. So Sn as let me take x1 plus x2. So what is the moment generating function of Sn t? That is the expected value of e raised to power t Sn. This is nothing but expected value of e raised to power t x1 plus x2. So therefore, this will be expectation of e raised to power t x1, e raised to power t x2. So let me take x1, x2 are continuous random variables. So e raised to power t x1, small x1, e raised to power t small x2 into joint density. But we know that x1 and x2 are,
Excuse me, sir.
yes,
In that we initially we thought we taken that x1, x2, xn are independent, no? So we can take directly e of e power t x1 into e of e power t x2 is equal to e of e power t x1 into e of e power t x2.
but how you are taking it, that I am explaining.
Okay, okay.
Just explanation why that already I have used basically in the previous lectures, but now proof I am giving for that. Directly how you are writing, once you have to explain that thing. Now x1, x2 are independent. That is given to us, let us say. Okay, so then this is joint will be product of their marginals because of independence. Okay, so therefore this will be integration. Let me take e raised to power t x2 f x2 x2 into integration e raised to power t x1 dx1 dx1 dx2. Just separating the terms. This is nothing but definition of basically expected value of e raised to power t x1. Once this will come outside, expected value of e raised to power t x1, but inside quantity will be this, which is expected value of e raised to power t x2. This is nothing but moment generating function of x1 at t1. This is the moment generating function of x2 at t xt. Okay, so we have shown that moment generating function of summation if x1 x2 are independent, then that can be written as product of their moment generating function. So this concept previously also we have used, but proof I have given this time because for that you required the definition of independence, etc., which can be explained when we have done the joint distribution. So that's why this is given here. Now using this concept we can give some of the proofs. For example, if x1, x2, xm are independent random variable, then if xi's are binomial ni comma p, then their summation is binomial i's from 1 to m ni comma p. So let me give proof of one of them. Let me give proof of the first one. So xi's are independent binomial ni comma p, i's from 1 to m. Okay, so can anyone I they are independent also. So can anyone remembers that what is the moment generating function of binomial distribution?
Q plus e raised to the power t p into e raised to power t.
Yes, q plus p raised to power t raised to power ni here. Okay, I is from 1 to m. Now let me take Sm as summation xi, I is from 1 to m, because they are independent also. So moment generating function of this will be product of their moment generating function. So therefore product of this will be product of this basically. So q plus p e raised to power t raised to power n1 into q plus p e raised to power t raised to power nm. So therefore this will be q plus p e raised to power t raised to power n1 plus n2 plus nm. So this is of the same shape, except that ni is replaced by n1 plus n2 plus nm. So clearly, by the uniqueness property of moment generating function, Sm will be binomial summation ni, I is from 1 to m, comma p. Okay, so in this fashion, we can show the some of the proofs. So if xi is Poisson with parameter lambda I and x1, x2, xr are independent, then summation of them is also Poisson. Xi is geometric, then summation of them is negative binomial with parameter m comma p. If xi is negative binomial, summation of the xi will be negative binomial. Xi is gamma with parameter alpha I comma beta. Then summation of xi will be summation alpha I comma beta. If xi is chi-square, then summation of xi will be again chi-square with parameter summation I is from 1 to m ri. Okay, in this fashion, all these proofs can be done easily using the moment generating function
Sir,
approach. Yes.
so in the gamma representation, the first term denotes the rate or the number of arrivals.
Basically, this will be your we have taken lambda raised to power alpha, gamma alpha, e raised to power minus lambda x raised to power alpha minus 1. So we have taken this thing lambda raised to power alpha, gamma alpha, e raised to power minus lambda x raised to power alpha minus 1. So uh, alpha will be same and beta, as I remember, is 1 by lambda.
Okay, sir.
So just a notation here. In some books, notations are given as alpha I comma lambda, in some by alpha and beta, and beta is 1 by lambda basically. Inverse of the rate basically, you are what you are saying. But it basically depends on how you are writing the density basically. So density is lambda raised to power alpha divided by gamma alpha e raised to power minus lambda x raised to power alpha minus 1. So alpha will be same and lambda will be 1 by beta. Usually in some books we take. Okay, so next is basically if we take x1, x2, xm to be independent random variables, if xi is normal mu I comma sigma I square, then summation of them will be summation mu I and summation sigma I square. Okay, so let me give the proof of one of them. So let me give the proof of the first, second will be in the same fashion. Okay, so xi is normal, mu I comma sigma I square, x1, x2, xn are independent. Then what is the moment generating function of normal distribution? Anyone remembers from the previous classes? This will be e raised to power mu t plus half sigma square t square. Okay, and we take Sm as summation xi, I is from 1 to m. Then the moment generating function of Smt is product of their moment generating function. So therefore, this will be e raised to power mu 1t plus half sigma 1 square t square, so on, e raised to power mu mt plus half sigma m square t square. Therefore, this will be e raised to power summation summation mu I is from 1 to m t plus half sigma square I is from 1 to m t square. So Sm will be normal with the mean summation mu I is from 1 to m, and variance as summation I is from 1 to m sigma I square. Okay, so because it is of the same shape, e raised to power mu t plus half sigma square t square. Okay, so just try to do the second part. Okay, just do the second part. I'm taking a break of 2 minutes. Just do this second part. Yes. So am I audible, students?
Yes, sir.
Yes, sir.
Okay. Okay. So okay. So I think second part is will be also will be in the same fashion.
Yes, sir.
Is it okay? Do you want the proof of that?
No, sir.
Okay, so this will be in the same fashion. Okay, so sorry for that. I have taken a break of just 2 minutes. Okay, so this will be in the same fashion because proof will be in the same fashion. You just have to do some adjustment here, and also you have to do as we have done when I given the proof of this moment generating function. In the same fashion, you can do that. You can easily get the answer.
Sir, I have one more method. Can you check if that's true?
Actually, you cannot share. You just send me. I will.
No,
I
sir,
will
it's
reply.
just I can say it verbally. It's small.
Just tell me.
Sir, can we do this like for if there is an AI xi, so we can take it as something else which is yi. So for yi, we can say that the mean would be AI into mu I, and the variance would be squared. The constant would be squared. So there would be AI square and sigma I square. Okay, and from the first statement, the summation, we can put the summation of sigma of yi. So we could get this. The mean would we would get the summation of AI mu I, comma summation of AI square sigma I square, and then we have the extra A naught. So the summation of A naught into that would not change the variance. It would only change the mean. So we could directly say that it is the normal of A0 plus dash dash.
One thing you can say that, for example, you are just saying that mean will be this and variance will be this, just easily using the previous methods. Mean and variance you can just calculate. Okay, and
Yes, sir. Yes.
but for the proof of that normal distribution, you have to basically uh, just you have to show that thing once at least that summation of AI xi will be normal.
Oh, okay, okay.
Once
Got it.
once you have to prove that thing, then only you can say for the next time that linear combination will be normal. Okay, so once you have proved once that linear combination will be normal, then you can say that after that you can say that uh, because linear combination is normal, I will just find out mean and variance. That will be sufficient. But at least once you have to check. Okay.
Sir, which
Okay,
means
sir.
that mean and variance we can sum anyway, but we also have to see for the shape that the shape remains of a normal distribution only.
Yeah, that is the thing I am saying. Na? At least once you have to prove that thing. For example, I have proved this once. That is the thing. The same thing I am saying that at least once you have to prove that linear combination of normal will be normal. Once you have observed this once, after that you can just say that thing that linear combination is normal. So I will just find out the mean and variance and okay.
But sir, I'm using the previous result. This one, this just above one. Summation of normal gives normal.
But AI mu I is absent here, na?
So for that I've taken a separate because AI into okay, so you are saying that if some constant is multiplied with xi,
You
so we have to prove
why you
that
will
is
give
also normal.
why you will give particular proof? You will give general proof first, then from there you derive this thing.
Oh, okay, okay.
Once you prove this thing, then after that you will derive these kind of things. For example, uh, I may be interested in, let us say x1 is normal mu1 sigma 1 square, x2 is normal mu2 sigma 2 square, both of them are independent. Then let me find out x1 minus x2. What is the distribution of x1 minus x2? So you cannot give the proof from here, you can give proof from here. Choose a0 as 0, a1 as 1, a2 as -1, a3 as 0, and so on. So this will be normal mu1
mu1 minus mu2.
minus mu2, then sigma 1
Sigma 1
square
square plus sigma 2 square.
plus sigma 2 square. Okay, so you are finding this using this result. Proof is also in the same fashion. So, but at least once you have to show that thing. Okay.
Yes, sir.
Sir, I have one more doubt.
Yes.
Sir, suppose we have one random variable as x plus x, where x is already known as normal random variable, and
X
suppose
plus
we have x plus x plus x, x1 plus x2 plus x3,
okay.
and suppose we have another random variable as 3x, in which there is a coefficient 3. So will both these have different properties, or will they be equivalent? 3x and x plus x plus x.
They are distributed as same basically. Distribution function will be same, na?
So
You are
because
writing 3x and x plus x plus x. So both are same.
sir, but when we do for the variance part, then for x1 plus x2 plus x3, it will be 1 square sigma 1, 1 square sigma square plus 1 square sigma square plus 1 square sigma square. That will be 3 sigma square. And for 3x,
But
we will
whether
use.
x1, x2, x3 are independent, x are independent.
Yes, sir, they are basically same in terms of n mu sigma square, but they are three different independent. Like x1 also follows normal mu sigma square, x2 also follows normal mu sigma square.
But you are not saying that thing, na? So, uh, okay. So you are saying x1, x2, x3 are there. But
Yes, sir.
once you have taken to be distributed same, then you can write 3x, na? But
Okay,
then
otherwise
they are
that will be
not. Then
different.
they are not independent, na? Once you are saying that they are distributed same, so then how they are independent among themselves, na? Okay, so in the same fashion, you can find out the total revenue for sales. So is that okay, previous one?
Yes, sir, I got it.
Their distribution is also there, na? Whether they are distributed same or not, distributed independence is there or not. So, okay, so all these concepts should be taken care. Okay, so total revenue for sale is, previous example was 80x1 plus 90x2 plus 60x3, the previous example. Okay, so now mean we have find it out of y, variance find out. Xi is normally distributed, the probability of revenue exceeds this value, this probability that y is greater than this value. So therefore we can do the standardization, y minus mu divided by sigma, this will be z. So z is greater than this value minus mean divided by under root of variance. So z is greater than this value. So this will be 1 minus capital phi of minus 3.31. That means probability z is less than equal to minus 3.31. So therefore this will be 1 minus capital phi of 3.31. But we know that capital phi of x plus capital phi of minus x is 1. So therefore this will get phi, capital Phi of 3.31, and this value you can see from the table as last time we are doing, because this will be normally distributed. Okay, so let me give first of all central limit theorem. So x1, x2, xn be independent and identically distributed random variables with mean mu and variance sigma square. They have common mean mu and common variance sigma square. Then summation xi minus n mu upon sigma by n root of n. That means xn bar, which is Sn by n, where Sn is summation xi. Then we are saying that this is Sn minus n mu sigma under root of n, which can be written as xn bar minus mu divided by sigma by n root of n. Okay. This random variable has approximate normal 0, 1 distribution for large n. Okay, so that is basically the central limit theorem. Okay, so let me give first example. Okay, so hard drives are packed 100 to a packet. Drive weights are independent random variable with mean 0.5 kg and standard deviation 0.1 kg. 30 packets are loaded to a box. Suppose we want to find the probability that drives on the box exceeds 1510 kg in weight, neglecting both packet and box weight. So let we denote xi be the weight of ith drive. I is from 1 to 3000. Then total weight is, because hard drives are packed 100 and packets are 30. So total hard drives are 3000. Okay, so therefore total weight will be x1 plus x2 plus x 3000. And what is the mean of x? Because they are basically IID. Okay, and independently identically distributed. So therefore they will be 3000 into 0.5, mean of one of them, because that will be summation of this, summation of xi. So therefore this will be mean of first one plus mean of second one plus mean of 3000. So that means 3000 into 0.5, and variance of x will be summation of variance of one of them. So that will be 3000 into standard deviation square, that will be 30. Then using central limit theorem, the required probability is probability x is greater than 1510. So you can, using central limit theorem, you can write down the total weight. This will follow the standard normal distribution. So z is greater than 1510 minus Okay, so because of this summation xi minus n mu by sigma by under root of n, or xn bar minus mu by sigma by under root of n. So here in this case we are writing Sn minus n mu by sigma by under root of n. So Sn is here this value, and minus n mu, that means expected value of x in this case, and under root of variance, under root of 30. Okay, so because all the quantities we have taken in this format, that's why. Therefore, z is greater than 1.83, and this is standard normal distribution. Z is standard normal, and 1 minus capital phi of 1.83, and this is the answer. Any question here?
Clear.
Okay, so proof I can give next time because time is less. So De Moivre's Laplace central limit theorem and bivariate normal distribution I can start next time.